The tool we have is using Z transform to deal with signals and functions. Why would we do that? Because usually in the transformation domain, in this case is our Z domain, it's easier to work on a system. Now, eventually we need to work on a system, a digital system, which is the input Xn, output Yn, and the system is indicated by the impulse response of Hn. So we have this mathematically, there is a convolution of X convolved with H if that is a linear time invariant system. So it can guarantee that the convolution works. In the transformation domain, we know because of Z transform property, a convolution becomes a product. So it will be very easy to find my system that is just in the format of YZ over XZ. So Y is any observation, X is its excitation. So you take this input, particular input, some particular output, a special case, you can measure that. And using those data, you can find out the system response. And then we do an inverse Z transform. This is not delay. This is what I want to say is inverse Z transform, and then become Hn. Okay, so we have something in the transformation domain, Z domain, and then we need to do some inverse Z transform back to the time domain. There are many other ways we do that using Z transform. Is we can check the property of the system, whether it's causal, whether it's stable, and that's a lot of things we can say about the system when we look in the transformation domain. Okay, so we have done some of the class theories. So let's put those into some real example problems. So example 1. What I have here is I have a signal Xn. Oh, this is a function. Can be anything. It's a signal that is in the format base half to the power n, subtract 3 to the power n. Usually we are dealing with causal system. So you put a step function just to indicate that is a causal signal. What does that mean? That's a step function. That means if n is less than 0, I don't have anything. Everything here is zeroed. So it's only starting from time 0. So it's a causal system, causal signal. Find the Z transform of that. So we want to find the Z transform of Xn. So what is that? Z transform of Xn. Now, if Xn is in this format, it's a base to the power n, where n is the time variable. It just index 0, 1, 2, 3. Time variable. If it's in this format, we know it's very easy to find the Z transform. Let me switch to board. We should already memorize that. But if you going back to the Z transform pair table, we find out if this term here is causal. And then what we have here is we just have a fractional expression there on the denominator order of 1 as a function of inverse of Z, as a function of 1 over Z, right? So we put in here. Now, whatever the base I have here, a to the power n, that is the parameter here. We have a name in the time domain. We call that a root of a polynomial, characteristic polynomial. We also have a name here. This a is actually a pole. Right? Why is that? Well, 1 subtract AC minus 1 equal to 0. That gives us a pole. So this pole is equal to A. When Z is equal to A, you plug in A inverse times A is 1. 1 subtract 1, 0. So yeah, that's a pole. Okay. So we know that it's very simple. Therefore, in this case, now we have 1 over 1 subtract half z to the power negative 1. Subtract, it's a linear operation, so we can work on the first term, then work on the second term. 1 over 1 subtract 3 times z to the power negative 1. Okay. If I want to write this out into a function of z, so all we need to do is we multiply numerator denominator by z. So it looks like that. Subtract z subtract 3. So some of software, including Matlab, is using as a function of z. But what we know is mathematically, we like to keep it as a function of inverse z. It's just very easy, straightforward from the time domain map to the frequency, map to the z domain signal. Okay. What is region of convergence? Okay, don't forget that the last part, region of convergence, is very important to complete the z transform. If you just give me stopping here, and you lost some credit because you really need to discuss about region of convergence. Given different region of convergence, the z transform format are actually different. Okay, so what is region of convergence? Well, this is a causal signal. If it's a causal signal, that's the exterior of a circle, right? It's just exterior of a circle all the way to infinity. And in this case, I got 2 poles. P1 is half, P2 is 3. So region of convergence exteriors of circle and all the way to infinity. So therefore, the region of convergence has to be this, 3. Has to be this. Okay, so those 2 parts give me this expression here, give me region of convergence. Then we have a complete answer for the Z transform. Let's use Matlab to verify that. Here, I'm using Matlab to verify that. In Matlab, there is a function called the Z-trans, which is here, called the Z-trans. Now, a very nice thing is it can use those symbolic format in Matlab. So we have defined a symbolic function, and if this is my function, right? Or you can put it x. Say this is my function. What I have, f is base half to the power n, subtract 3 to the power n, right? That's exactly what we have. And then I want to find out what is Z transform. So let me copy this into the command window and run it. Okay, so there we go. It gave me the f is in a symbolic format. You just write out this function. The answer is the Z transform. Z transform is Z over Z subtract half, subtract Z over Z subtract 3. That's exactly what we have here, right? This is the function as a function of Z. As a function of Z, that's what we have here. These steps. So exactly what we have in the Matlab. So very nicely we can verify that in Matlab using symbolic form, Z trans. Okay. All right. Example 2. We want to do xn as a function or a signal is a cosine omega n, where omega is a constant. It's just some frequency in radius. And we also have a causal system. Just make sure that's causal system. We times the step function. Find the Z transform of xn. Find the Z transform of this function. How do we start with this problem? Now we have a cosine function. We feel good if the function is in the format of a to the power n, something like this. That's if it's causal. We got a base, and we know that's a root, so it will be a pole. Very easily, we can directly write the Z transform. Now you give me a cosine function. What can we do? I also want to make it like a format like this, to the power n. So cosine function using Euler identity, we can write this out into half exponential e That's a base e to the power j omega n, right? Plus half e to the power negative j omega n. That's my cosine function using the Euler identity. And it's a Cauchy signal. So now we have here, I have a base where the base is e to the power j omega. Omega is a constant. And then this term to the power n. So that's what I like. It's the root like this. Okay. So when I have this, I can do the z transform, xz equals to, working on the first part, half, and the same thing, I say just 1 subtract a pole, which in this case e to the power j omega times e to the power negative 1. Okay, so there's this part. This part is my root. So this part I put in here as my coefficient in order to make sure that I have a pole e to the power j omega. The second part is half 1 subtract e to the power negative j omega c to the power negative 1. Okay, that's it. If you give that, it's already the final answer. It's z transform. But let's try to make all these coefficients real. So here is a complex number. Make it to real. So do some calculations on that. So we have we just putting these two parts together. We have 1 subtract e to the power j omega c negative 1 times e to the power negative j omega c negative 1. And then on the numerator is 1 subtract e to the power negative j omega c negative 1. And the other term is plus 1 subtract e to the power j omega c to the power negative 1. Okay, so this is, continue with that, just a few more steps. So we got a 2 subtract. Now I have those two exponential e to the power something, e to the power something. And again, using the Euler identity, I find out that's 2 cosine omega c to the power negative 1. Sine and sine, they canceled out. So I get 2 cosine. On the numerator, that's 1 subtract e j omega subtract z negative e j omega c to the power negative 1 plus c to the power negative 2. And all this and this, they multiply, that cancel, it becomes 1. So I got that. And just let me write out a few more steps. So we have 1 subtract cosine omega c negative 1. Here I got a 1 subtract this and this. Again, that's Euler identity. It becomes 2 cosine omega c negative 1 plus c to the power negative 2. Okay, so that's the answer that we will have with all these coefficients becomes real. So this is cosine omega, it's real. Cosine omega, that's real. And we can actually using the lookup table to directly find that. But if I'm making this very nicely base e to the power of j omega, then we can using the root and the pole, using that to easily find the solution for the z transform. Okay. Lastly, I just make everything is a function of z, so I can check in Matlab. So multiply by c squared on both numerator denominator. We have c squared subtract cosine omega z. Denominator is z squared subtract 2 cosine omega c plus 1. Okay, that's the answer that we should have. Now let me using Matlab to check. So Matlab, these 3 lines. So symbolic is I have n omega. I put a w here, but it's just a symbolic is a constant. If the function is cosine omega n, I want to find out the z transform. In Matlab, by default, what you are dealing with is a Cauchy function. If it's really anti-Cauchy, you have to find this solution that you substitute with u negative and negative 1, using that to calculate. So we find out this is the answer, right? This is the answer is z transform z times z subtract omega cosine omega over z squared subtract 2 cosine omega z plus 1. And that is the answer we have here. That's the answer we have here. So indeed, we check that that is correct. The Z transform. Okay. Now we look at the partial fraction expansion. For inverse Z transform. Partial fraction expansion for inverse Z transform. So example 3 we have here is I already have a function in the Z domain. Xz equals to 1 plus Z to the power negative 1 subtract Z to the power negative 1 plus 0.5 Z to the power negative 2. Doing a partial fraction expansion, we did one problem before. Right? The denominator is very easy to factorize into 2 terms, a product of 2 terms. Each term is first order, so it's easy to find poles. In this case, actually, those 2 poles are complex number, so it's not that easy to directly factorize the denominator and put into 2 terms. So what I meant is, if I can very easily find out, one subtract P1C plus if you can very easily to factorize into this term, and then you just multiply this, and adding together, make sure all these coefficients are equal, and you putting into the equation set and find A1 and A1, A2, excuse me, A1 and A2. Find those 2 constant, which is the remainder of my long division. But in this case, P1, P2, they are complex numbers. So I'm going to use what the book suggested, the way how to do the partial fraction expansion. So what we have here is we have xz divided by z, and then make it everything as a function of z, as a function of z. So we have, let me just 1 over z, because this is a divided by z term, and make a function of z. So z squared plus z over z squared subtract z plus 0.5. Okay. Z squared subtract z plus 0.5. Now I want to find the poles. So we will find the roots of the denominator. Equal to 0. So what can we do that? Well, it's a quadratic equation. It's a quadratic equation. If this is a, b, c, we know the root is p1, 2. The root is negative b, positive negative square root of b squared subtract 4ac over 2a, right? This is quadratic equation, how we calculate. These are the coefficient. A is 1, b is negative 1, c is 0.5. Therefore, we find out using this formula, we find out P1, 2 is equal to 1 over 2 part of negative j 1 over 2. So these are the 2 poles. They are a complex conjugate pair, but it's a complex number. So actually we have, if you draw this on the Z domain, this is real, this is imaginary. So I get a half here, positive j, half, and a negative j. So I got 2 poles here, P1 and a P2. They are within the unit circle. This circle is unit circle. All right, so now how can we calculate? We know I got those 2 parts, and I want to find the remainder, A1 and A2. I have it here over C. This is equal to A1 over C subtract P1 plus A2C subtract P2. I want to find those A1 and A2. In this case, it's a function of Z already coming. It's coming from this, right? And I know P12 is given in the box. To find this, using what we have in the book is A1 the first parameter is equal to, I multiply this by z subtract p1 multiplied by xz over z, evaluated at z equals to p1, okay, right? So once you do this multiplication, the first term, z subtract p1 canceled out. What you are left is a1. Second term is I multiply by that. You have some values. Now I need to make sure that I plug in z equals to p1. And if you do that, you multiply by z subtract p1, because this is something, if you plug in z equal to p1, this should be a 0. So you multiply by 0. So the second term, when you multiply by z subtract p1, it goes away when you evaluate at point z equals to p1. Now, when we calculate that, of course, I cannot use in this term. It's not going to give me anything. It's that we still have those unknowns a1 and a2 in it. What I'm going to use this term in the circle in this term. This is my xz over z, right? I'm going to use that term. So plug in here, and this is equal to z plus 1 over this. Well, this I already have, actually I have a z sub, this on the denominator, z subtract p1 times z subtract p2. You already multiply by that, so it only leave 1 is z subtract p2, right? Well, what p2 is, we have here is half subtract j times half, okay? And this, I will evaluate at z equal to p1. Okay, let me say that again. So I'm using this part. This part is z plus 1 over z subtract p1 times z subtract p2. This is this part, right? And the p1, p2, now we have a number, p1, p2 as in this box. We already calculated. When you multiply by z times p1, so z times p1, this will cancel out. I have this part. Of course, p2 is one of the numbers is here. So z plus 1 over z subtract p2. And then I evaluate, I'm putting this value of z equal to p1, where p1 is also a number. That's positive half plus j times half. And then we have all these numbers, so I can plug in now. Z is p1. P1 is half positive j plus 1 over z1 here is half plus j times half. Subtract p2 is also a number. Subtract p2 is half subtract j, this. And that will give me the answer, and I calculated this will become 1 over 2 subtract j, 3 over 2. After some calculations, we find out this number. So this is A1, the parameters, the parameter on the first term, A1. Similarly, I can do for A2. A2 is z subtract p2 times xz over z, when z is evaluated at p2, right? So we have multiply z plus 1, and we cancel out z subtract 2, so there will be z subtract p1, evaluated when z is equal to p2. So we plug in, z is p2, so z is half subtract j plus 1, z is p2. I plug this in, and then p1 I know, p1 has number, is a half plus j half. So calculate that, I will find the answer for A2. So we got this part. Then we plug in, we have done for the partial fraction expansion. Right? Now, once we got that, how to find the inverse Z transform? Once we got this part, how to find inverse Z transform? Let me squeeze here. X. Remember, this is xz over z. equals to A1. I just find it. A1 is this number over Z subtract P1. I got a P1 number, right? I'm just using those shorthand, but I know I have all these numbers ready. P2. How to find the inverse Z transform? Well, in this case, you have to multiply by Z on both sides. So we recover becomes this. P2, Z to the power -2, right? And I know I already calculated P1, P2. I calculated A1 and A2. Therefore, using the Z transform, you can either go for the table, or it's very easy. This is just first order on the denominator. It's very easy. So the first term is A1 times what? We should know that, right? P1 is a pole, so it's a root. It's P1 to the power n plus A2 times P2 to the power n. And of course, if you are dealing with a causal signal, and then we have this unit here. So it's very simple. That's the inverse Z transform. And we have all these A's and the P's ready with numbers. Okay, so that's the example for a partial fraction expansion. Example 4 is also doing an inverse Z transform. I got the function as a function of Z, looks like that. 1 subtract Z to the power -1 squared. Now, in this case, I know I have 3 roots, P1, P2, P3. However, P2 and the P3, they are identical because I got this term. Right? So we have here is P1 is equal to -1, according to the first, and a P2 equal to P3 equal to 1, according to the second factorized term here. So I have a pole of multiplicity 2. Therefore, we know when we're trying to do the partial fraction expansion using the xz over z method, we have to do some little trick to deal with that. So let's work out this problem. Same thing, we have xz over z becomes z squared. Z plus 1, Z subtract 1 squared. Factorize that into 3 terms. So A1 over C plus 1 plus A2 over C minus 1, no problem. But I also have a third term, which is A3 over C subtract 1 squared. I have this third term because I have a pole P2, P3 of multiplicity 2. So I got those 2 later terms. Using the method we just showed, to find A1, it's very simple. A1 is we multiply the entire thing by Z subtract P1, which is Z plus 1. Right? P1 is -1 here. So we multiply this entire thing, xz over z, by Z subtract P1, which is Z plus 1. And evaluate it on Z equals to -1, on Z equal to P1. So we find out this is one. Once we do the multiplication, we find out this is again I'm going to multiply by this guy. Right? This is my xz over z. So multiply by this. We have the numerator z squared, denominator is z subtract 1 squared. Z plus 1 cancelled out. And we evaluate at z equal to -1. So we plug this in, it's 1, and this is 2 squared, it's 1 over 4. So we find out A1 is 1 over 4, very easy. Now A3 is also quite easy. A3, we can multiply this xz over z by z subtract 1 squared, xz over z. And then we evaluate z equal to P3, which is z equal to 1. And using this term in the circle, we have numerator z square over then denominators. We cancel that. Z subtract 1 square canceled out. So we have a z plus 1. Evaluated on z equal to 1. Therefore, this is 1 over 2. So A3 is half. That's very easy. And the only tricky part is A2. A2. A2, remember that we need to do is I need to multiply xz over z, multiply by this in order to cancel those poles. But for this term, I only want to check A2. So therefore, I need to do this this term dz. Right? Take a first derivative, and then evaluate it at z equals to p2, which is equal to 1. Right? This is what we have shown a few class before, that how we find A2. And let's work this out together. It's not that difficult. So we have a d over dz. So this part we just calculate. That's z squared over z plus 1. Right? This is this part here, right here. Evaluated as z equals to 1. Let me just evaluate this. So to do this differentiation, we are using the quotient rule to do that. So we have, let me write in some detail. For the numerator, on the numerator, and then times the denominator term, subtract the numerator times dz over the denominator term over the denominator term squared. Right? This is quotient rule. So we find out the first part is this is 2z, z plus 1, subtract z squared times 1, so I'll leave it there, over z plus 1 squared. Okay, so I know this is, you can calculate, you can express this out or easily because I'm evaluated at z equal to 1. So you plug in this 1, so it becomes 2 times 1 times 2, 4 subtract 1, so it's 3, over 1 plus 1, 2, 2 squared is 4. Okay, so I find out A2 is 0.75. Therefore, my answer for the partial fraction expansion xz is equal to A1 times 1 over 1 subtract p1z to the power -1. Now p1 is -1, therefore plus c to the power -1. A2 is 3 over 4. 1 over 1 subtract c to the power -1 plus A3 is half. We calculated before. So we got here A3, this term here is z -1 over 1 subtract z -1 squared. Well, why do we have that? Well, what you need to do is you need to put in this part. Then because I need to get rid of the over z, so you multiply by z of this part, and then make sure it's a function of z to the power -1. And then you find out we actually have on the denominator, we got 1 over z -1 squared. On the numerator, we have a z to the power -1. So it ends up like this. All right. Let's find its inverse z transform. That's what we want. I want to find xn. Inverse z transform. Okay. Inverse, if I have the term here, what I need to use 2 lines of this inverse z transform. The first one is here, right? I got something on the denominator, it's order of 1. Remember, it's a subtract a. If it's subtract a is my root, so it's a to the power n is this term. And another line, I'm going to use this one. This one is 1 subtract a, z to the power -1 squared. And then on the numerator, I have a z to the power -1. we should have the same coefficient A. If I don't have the same coefficient A, just put this constant to the beginning and make sure those two coefficients, they are the same. That's the root of A. And then that will give me a format which is n times A to the power n. So check back here. Now we know that this first term is 1/4 times root here is -1. -1 to the power n. The second term is 3/4. Root is 1. P is equal to 1. So I'm just leaving it here. It's 1 to the power n. The third term is half. And I'm checking the coefficient. This coefficient here is 1. Coefficient here is 1. So fine, that's 1 to the power n. If the coefficient here is not 1, actually this is not 1, this is half. So I'm just put a half at the beginning and in front of that. So it's not a big deal. And then we have n, right? We have n times A to the power n, right? A is 1. A is 1. But we still have n. Don't forget we have n. So n times 1 to the power n. So this 1 to the power n, I can't neglect it. So I got that. This is my final answer of the inverse C transform from the original overall function like this. Overall function like this. Now let's check that in Matlab. Remember that it's 1/1 plus c -1, 1 minus c -1 squared. So in Matlab here, I got it here. So the system is the system capital X is 1 over is what I write 1 plus c to the power -1 times 1 subtract c to the power -1 square. And of course, when you in Matlab, it gives you as a function of positive z. So it ends up like that. And then I do an inverse C transform of capital X. And that's what we have. This is exactly the answer we got. If it's causal, by default, it's a causal system. So we have a half times n, -1 to the power n, divided by 4, and plus a constant 3/4, which is that what we have here. We just checked that. This is the answer that we have. Okay, so very nice. We got this part, and we're using the Matlab to check with this answer.